Okay, so now I'm going to shift to a lighter subject. We're going to look at lazy learning, which is sounds good, at least to me. And the idea is that so far we saw these eager learning algorithms where we try to fit the parameters of our model, but there are an alternative approach which does not try to fit the model and postpones all the computation to the time when we want to query our classifier, for example. So we're going to see an example of a lazy classifier, k nearest neighbor, and we're going to see also lazy learning applied to regression and other density estimation, probability estimation. So the basic idea so far we saw in the polynomial regression and logistic regression, we have a hypothesis space, we have a model that describes the hypothesis space with some parameters. We train the model by adjusting the parameters, and after training we can throw away our training data because now we have the trained model, and that's all that we need. So this is eager learning, where we're trying to extract as much information as possible from our training set, and then we keep only the model and not the training data. Then the answer we obtain when we query the model is based on the parameters of the model, and the model doesn't need to look up the training data anymore. With lazy learning, we don't really have a training set. We just store the training data. And it's when the classifier or the regression model, so on, is queried, we do the computation and give an answer. So usually, in this case, we don't need a model to represent the hypothesis class. We are not adjusting these parameters, we are just storing the data. We don't train, just keep the data and do all the computations at query time. So let's see an example in k nearest neighbor. For this classifier, we need a training set with the features and the class label, and we just store that training set. Then, every time we have a new point that we want to classify, we look at the k closest examples in our training data that are nearest to the point we want to classify. And we simply give the label of the majority of those closest examples. This is lazy learning. We are not adjusting a model. We don't even have a model for representing the hypothesis class. The hypothesis class here is all the possible sets of training data that we can have, but we are not explicitly representing that with a model. We are not training anything because we just keep the data and wait for a question to go do the computation, and the answer is based on the data that we have. So let's see an example here. This is an example of what would happen if we use this training data, so this set of blue and red dots, and we use k equal 1. So this means that we are only looking at the nearest neighbor, and when we want to classify a point here, let's say, the nearest neighbor is this one, so everything that falls here is classified with that label. Everything that falls in this region is classified with that label, and so on. So with Euclidean distance and k equals 1, this is actually a Voronoi tessellation of the space occupied by the training set, which is, for each point, we have the region of points that are closest to that one, and we have these hyperplanes separating the different regions. So in this case, in 2 dimensions, it's just a straight line. If we increase the value of k, this gets a bit more complicated, but what we're doing here, say for k equals 3, is that on points here, we are looking at the 3 closest neighbors and assigning the class of the majority. So in this case, the 3 closest ones have 2 reds and 1 blue, so this part is red. When we go over on that side, we start getting other blue neighbors, and so the class label changes. Now these cutting edges between the different regions become a bit more complicated, and as we increase the values, we get a more complex picture here. But the idea is that we always have a piecewise linear frontier. So if we are using Euclidean distance, the frontier is always made out of a set of straight lines in 2 dimensions or a set of hyperplanes in n dimensions. But exactly how the frontier is determined depends on how many neighbors we are looking at and what is the distribution of our training set. So if we have a lower k value, we are looking locally at the closest neighbor, and so we can have a more intricate cutting between the groups of points. Because for classifying each point here, we are looking only at the closest neighbor, and we can see these distinctions, for example, between these two, and so on. If we increase k, we are looking, for example, here at the 25 nearest neighbors, and so we are, for each point, looking at the majority votes of the 25 points that are closest. And this can smoothen out a bit the frontier and make it less dependent on local changes and look more broadly at what happens around. So this is one parameter that we can adjust in k nearest neighbors to try to minimize overfitting or try to optimize our classifier, and we can do this in the same way with cross-validation. But first, I'm going to show a simple implementation of the k nearest neighbors classifier. You're not going to use this, you're not going to implement it because you already have it on scikit-learn and it's a lot more efficient. But the idea is that showing the code, you understand a bit better the details of the algorithm. So the first thing that we need when we're looking at the nearest neighbors, we need some measure of distance. If we have categorical data, so if we have something like a profession or sex or something like that, where we have categories, we don't have numbers in a continuous range, we can use something like Hamming distance, which assigns a distance of 1 if the feature is different, or 0 if it's the same. So we can just count how many, between 2 examples, how many values are different in the feature. If we have continuous data, it's usual to use some p-norm or Minkowski distance, which is defined in this way. We have the p-root of the sum of the modules of the difference between the feature values raised to p. So this seems a bit complex, but we have some useful, very used cases, which is Manhattan distance, where this is p is 1, so you just take the modules of the difference and sum it. Or you have Euclidean distance, where p equals 2, so you square all the differences, sum, and then compute the square root. So these are just 2 examples, but this is a more generic, the Minkowski distance. You can adjust that parameter. So this is an example of using Minkowski distance with k equal 1. So this is the Minkowski distance with p equals 2 is the Euclidean distance. These are other examples. This is Manhattan distance. You see the frontiers now are different because we are counting distances as if we were going along the streets of Manhattan, so we always take 90 degrees turn. And if you adjust the parameter to something like, say, 0.7, you get something a bit weird because you're using different distance measures. But the idea here is that although we usually use something like Euclidean distance, this is very sensitive to how you're measuring distances. And it becomes important when you have different kinds of things, say, like height and weight and age, which have different scales. And so how you measure the difference between those vectors can be very critical to these kinds of classifiers. So we can write a function to compute the Minkowski distance. We use a default value of 2 for p. So this is how you can do this in Python when you're declaring the parameters for your function. You can assign default values here. So if the argument for that parameter is not given, it has a default value that will be used. So here we have a matrix with all our training data. This is a matrix which has 1 example per line, and the number of columns is the dimension that we have our data in. This is a point, is a vector with all the features of 1 point. When we do this subtraction, the NumPy library will do broadcasting between the vector and the matrix. So you can see a better explanation of broadcasting on the documentation, but the idea is that when you have two matrices or two arrays of n dimensions, NumPy will match the last dimension first, and then the one before last, and so on, until one of them has no more dimensions, and it just broadcasts everywhere. So in this case, we have a matrix with, let's say, two columns, if it's in two dimensions, and n lines for all the examples, and we have a vector of two values for one specific point. So this has a length of 2 in the last dimension, it's the only dimension, and the matrix also has a length of 2 in the last dimension, which is the column. So this subtraction will subtract this vector from each row on the matrix and give us a new matrix with all those differences. So you don't need to use for loops for this kind of operation. As long as you have the right dimensions on your array, you can do it all in one go. And then we can apply the power operation here to 1 over p, so this would be the square root in this case, and we sum everything along the dimension of index 1. Well, you can use an arbitrary number of columns or even dimensions. So the requirement is only that you can align the two arrays from the last dimension backwards. So if one array has a length of 2 and is a vector, and the other array is a matrix with 2 columns, it can align the 2 elements with the 2 columns and then broadcast over all the rows. Okay? So here we are summing along the direction of the columns. We get an array with all the sums for each row, and then we compute the square root in this case. So we now have the distance between this point and all the points in our data set, and we don't need to use loops for this. So this takes a bit of practice, but if you try it out with some matrices just to see how it works, then it can save you a lot of time when you are implementing anything, because it's easier to do these operations using the NumPy array. So now we need to find the k nearest indexes, the k nearest examples. We just take the distances to all of them, and this argsort function returns the indexes that would sort the array. So we have the indexes that would sort the array increasing from low distances to high distances. So basically, we have the index of the nearest neighbor, then the second nearest neighbor, and so forth. If we take the k first elements of these indexes, we have the indexes of the k nearest neighbors. And then for the classification, we can use this mode function. The mode is the value that appears most often in a set of values, and we apply that for the labels with the indexes of the closest neighbors. Okay? So this is just because the mode function actually returns the arrays of the modes and how many times each of them appears, but we only want the first mode, so the one that appears most often, so we don't need the whole array. But in any case, what we're doing here is we're computing the distance to all the training sets, then we're finding the closest k, and then we use that set of the k closest neighbors and find the majority votes for the class. And this is the class that we assign to the example that we were showing. Okay, so now what can we do to use k nearest neighbors? One thing we did so far was that preprocessing where we do standardization or normalization to bring all the features into the same range, or when we do regression to bring all the values into the same range. With distance methods, we have to be careful with this because it may insert some distortion in our data. For example, if you have features describing people with, say, monthly income, age, weight, height, and so on, then you probably need to do standardization because those values are in very different scales. And if you don't bring them all in the same scale, then, for example, income, which may be in the thousands, will have a much larger weight for the distance computation than age, for example, which would be less than 100. On the other hand, if your data is actually, say, coordinates, 100 meters north, 20 meters east, or something like this, if you do standardization, you will deform the measurements that you're doing, because they're all in the same scale, and if one of them tends to be shorter than the other, maybe that's meaningful for the distances you're computing. So you need to take care when you're using methods based on distance to decide whether or not you should preprocess the values, or how you should preprocess them to avoid inserting distortions in your data. Okay? So generally, you should normalize or standardize to keep everything in the same scale. Sometimes, if things already are in the same scale, you should take care not to distort them by, say, subtracting the average, or dividing by the standard deviation, or something like that. So let's see an example. We have this data set, and we want to find the best k value for our k nearest neighbors classifier in this data. So we're going to load the data set. We set aside the third of the points for testing, so to get an unbiased estimate of the true error in the end. And now we're going to do cross-validation to test different values of k. We're only going to use odd values of k, so 1, 3, 5, and so on, because we have two classes, and this way we avoid the problem of having a tie. So if we use a k of 2, and there are points with two different classes, then we don't know which class to assign to, but if we use only odd values of k, we can avoid that problem. We're going to compute error. Error is 1 minus the accuracy, so the fraction, the error is the fraction of misclassified. The accuracy is the fraction of correctly classified examples. Now, it's important that we're not going to use the test error to decide which is the best value of k. Because if we use the test error, it will no longer be unbiased, because we are choosing the smallest one. However, we can compute the test error for all the examples and plot it. It's not a problem. Nothing wrong happens if we look at the value. The thing is that if we are using the value to choose something, then we bias everything. So this is an example for this data. This is the cross-validation error here in red. This is the training error in blue. And one thing that you can see with k-nearest neighbors classifiers is this characteristics pattern for the training and cross-validation error. When we have a k of 1, the nearest neighbor of a point in the training set is always the point itself. Unless you have points overlapping in the same coordinates, when you measure the training error, you get something that is 0. Because for each point you give as an example, that point is already stored as part of the training set. So this is one, it's a bit different from what we usually see. When we have k equals 1, we start right at 0 in the training error. Of course, since we are always looking only at the nearest neighbor, outside the training set we can have a lot more error. As we increase k, we start increasing the training error, but we start decreasing the validation, the cross-validation error. We can also see that we start decreasing the test error, and the test error is not exactly the same as the cross-validation error. So choosing the value with the lowest cross-validation does not guarantee, with the lowest cross-validation error, does not guarantee that we get the value with the lowest test error. And this is something that you should keep in mind when you're doing this kind of work, because if you run everything again, since you are splitting at random between training and testing and between the various folds in cross-validation, you can get slightly different graphs. Okay. So it's very easy to cheat if you're looking at the test error and you run again and again until you get a very low test error and say, wow, I have a very good hypothesis here, this is a great classifier. But what you actually did was to use the test error to make your final decision, and maybe it's even worse, that one that resulted from any of the previous ones. The thing is that each time you run, all these error estimates are sampled from what they could possibly be. And if you choose the smallest one, you are biased towards lower values, so you may be deceiving yourself. So this is just basically to give you a warning. It's not a problem if you plot the error. The thing is that when you choose a value choose the smallest one, then you are biasing everything because you are deliberately choosing a smaller value. So and this would be the best one. Use k equals 9, somewhere around here. And now we train with everything. Note that the cross-validation error is an average of the different folds. And when we want the final classifier, we store all the training data in this case. So we are no longer splitting in different folds. And now to get an estimate of the true error, we test it with that third of the points that we left out in the beginning. One problem with these methods that are based in distance is this curse of dimensionality. Actually, it tends to be a problem in general when you go to very higher dimensions, but these classifiers and these methods are especially susceptible to this. And the idea is that when you are looking at the neighborhood of a point, you have this core region around the point, which is more or less safe because that's very close to the point, and then you have this border region where the examples could be close to another one in your training set. The curse of dimensionality is due to how much volume this frontier region will occupy as you increase dimension. And this is not very intuitive. So let's say that we have, in one dimension, we consider the border to be 2.5% in one side and 2.5% on the other, so a total of 5% of the size of the region. This would be the place where things are a bit uncertain. When we go to 2 dimensions, this will actually occupy 10% of the area, because now we have this ring of 2.5% in width, but it's the outermost part, so it has a larger area. If you go to 3 dimensions, it occupies 15% of the volume, and so on. So actually, when you reach around 20 dimensions, most of the hypervolume you have there is in the border region. The more dimensions that you have, the more of the volume is at the edges, and the smaller the fraction that is at the core. So if you have these kinds of methods that depend on measuring distances and work best when you are close to the known examples, but make more mistakes when you are at the edge, then it's bad to use a lot of features, because then you start having this problem that everything is on the frontier, and so you get more errors. Okay? So this is called the curse of dimensionality. As you increase the number of features that you use, your method may start to work less well and reduce the performance. So let's see how we can use this lazy learning approach, the k-nearest neighbors, for regression. We use it for classification by taking the majority vote of the class labels around one region, so the k-nearest neighbors, but we can do that also for regression by taking the average of the k-nearest neighbors. So if we have a k-nearest neighbor regression with k equals 1, then each of these blue values is simply the value of the nearest neighbor in the training set. We keep all the data in the training set, and then when we want to compute a point, we look at the nearest one and use that value. If we have a higher value of k, we use the average of the k nearest neighbors. So in this case, we look at the 11 nearest neighbors and we average them to compute each value, and so forth. As you can see, this always gives us these steps here, these discrete changes, because at some point we are changing which are the closest neighbors. So we have a set of neighbors here, but when we reach this point, now a few of these disappear and new ones appear, and so we have a step. We don't have a continuous function. We are changing in steps here. We can solve this by, instead of just considering the k nearest neighbors, we consider all the points, but we give more weight to the ones that are closest and less weight to the ones that are furthest away, but we do so in a continuous manner. So for that, we can use a kernel function. A kernel function in this context is simply a function that is greater or equal to 0 over all its domains. The integral of the function over all the domain is 1, so the area of the function is 1, and the function is symmetrical around 0. So here are some examples. We can use a uniform distribution, a triangle, a Gaussian, cosine, and so on. There are many different functions that we can use as kernel functions that have these properties. And these functions can be used to weight the different examples depending on their distance. For doing this kernel regression, we need the kernel function, and then we need a way to weight the different examples using the kernel function. So basically, we use a kernel and an estimator. These are some examples. This is the Gaussian kernel, the Gaussian curve function. This is the Nadaraya-Watson estimator. Is simply a weighted average using the kernel. So each point weighs as much as the kernel value when considering the distance in the x dimension between the value of that point and the point we want to evaluate. And then we divide by the sum of the kernel contributions. We have other estimators. For example, this Priestley-Chow gives different weights to points that are more separated or closer together in our data set. So this adjusts for when the training data that we kept is not regularly spaced along the range that we are looking at. But basically what we have is this kernel function and a way of weighting points with the kernel function so that we can do a continuous regression using the data points that we have stored. So for example, here we have this Gaussian kernel. It simply computes the Gaussian function given an input value u here. So this is the distance between, generally the distance between the x coordinates divided by this parameter that allows us to make the kernel broader or narrower. And then we have this Nadaraya-Watson estimator that just goes through all the values that we have, all the points that we have stored, and adds each one weighted by the kernel. So basically, we compute the kernel value for that point, multiply it by the epsilon, and we also add all the values of the kernel to get this weighted average. And this is an illustration of the result. We can use that age parameter here to make the kernel sharper or broader. So if we use a large value of age, we can broaden that curve because now we are dividing the distance between the points by a large value, so it becomes the u value becomes closer to 0, and it takes longer to change the value of the kernel. If we use a low value for age, we can make it change faster, and so the kernel becomes narrow. If we use a narrow kernel, then the regression is looking at the points in a narrow neighborhood of each of the points that we have, and so the curve becomes more intricate and changes more as it passes close to each point. If we broaden the kernel, we are averaging over, we are giving more weight to points that are far away too, and so the curve becomes smoother. Note that we don't have a model here, so we don't have the parameters for the curve. We keep the data, we have that age value that we chose, we can do that with cross-validation, for example, and then we simply compute the weighted average of all the data points that we have using the kernel function and the estimator that we have to compute that curve. Okay? So this is an example of a lazy regression where we store the value, we just choose that age parameter, and only at the time when we need to compute the values are we going to look at our data and do the calculation. We can also do this for density estimation. Density estimation is basically what you do when you do a histogram. You have a distribution of points, and you want to compute where in the distribution you have a larger number of points or fewer points, and so on. The problem with histograms is that it's discontinuous and changes a lot with the size of the beans. So if you use smaller beans, you can have this green histogram here. With larger beans, you have this yellow here, and it can change shape depending on where in which bin each point falls in. We can use kernel functions to do this continuously. And the idea is that if we have these points distributed here along these values, and we want to represent the distribution, the density of points in different regions, we can use the kernel function centered on each of the points. For example, in this case, we have Gaussian kernels, and then sum all the values of the Gaussian kernel. So each Gaussian kernel contributes 1, the total area of that Gaussian. When we sum it, we have this total area equal to the number of points that we have here. But now we have higher on this part where we have a more larger concentration of points and lower here. We're going to see this in a bit more detail next week when we talk about the naive-based classifier. But you can do this easily with the kernel density class in scikit-learn. You just give it the data point. So actually, when you call the fit method, this is a lazy learner. It doesn't do anything. It just stores the points. It's when you call the score samples or want to score the probabilities, that's when it computes the values for those points. And these score samples returns the logarithm of the height of this function. So basically, the logarithm of the probability of finding each of these each of these values there, based on the density distribution of the data that we gave for training. And this, the logarithm of the probability is useful when we are combining different probabilities, because if you're trying to multiply very small values, you can get floating point underflow very easily. But when you do the logarithms, you just sum everything and it works better. But we're going to see this in more detail next week. So to sum up the lazy learning method, you don't fit parameters of a model, you just store the data and you postpone any calculations for when someone asks a question. And we have examples here of the k-nearest neighbors classifier, when you look at the k-nearest neighbors and use the majority votes to assign a label to a new example. The regression, doing the same thing and averaging, and also these kernel methods that are similar. You also store the training data, and then when you have to query and ask for a value, you're going to look at all the training data, add up the kernel functions, and give the result. When you're using distance-based methods like k-nearest neighbors classification or this kind of k-nearest neighbors regression and so on, you have to take care because as you increase the dimensions of the number of features that you have, this is not very intuitive, but the kernel area around each point becomes a very small hypervolume relative to the frontier. So you can get some problems when you have too many features with these kinds of methods. So this, in these sections of Alpaide and Mitchell and Markland, you have some talk about these classifiers and the kernel methods. I recommend that you read them. And if you have questions, we have some time.